Use the definition of logarithm to simplify logarithm expression. Special property of logarithm. For any positive real number b, where b is not equal to 1, the following holds true. So these are the true statements. Log of b to the power of r with the base b is equal to r. So when the base of the logarithm matches the base of the exponential here, the whole thing would be equal to r. It should make sense too, because if you look at the property again, if I have log of x with the base b is equal to y, if I wanted to convert this to the exponential, that's the same as b to the power of y is equal to x. So look what we have here. Here we have b to the power of r is equal to b to the power of r. So this should be a true statement. So as this one, b to the power of log of b to the power of r also equal to r. So as long as the base of the exponential and base of the logarithm matches, the whole thing would be equal to this r. What's log of b with the base b? Well, looks like the exponent here is 1. So according to this, log of b would be equal to 1. So therefore, a good example of that would be, what's log of 10? Log of 10 must be equal to 1, because when you don't write anything down here, you assume that the base is 10, and here the base of the logarithm and this exponential is the same. So 10 is the same as 10 to the power of 1. So that's why log of 10 is equal to 1. Here we have log of 1. What's log of 1? Well, if I write 1 as b to the power of 0, so anything to the power of 0 is equal to 1. So log of 1, it really is log of, if I replace 1 with b to the power of 0, because the base is the same, now this whole thing would be equal to 0. It matches this number. So these are the ones that you want to remember it, that log of 1 is equal to 0, log of b, as long as the base is the same, is equal to 1. But you really can drive this very quickly using the fact that we can convert the logarithm into its exponential and to get these results. So let's take a look at these examples. Use the special properties to evaluate each expression. Here we want to evaluate log of 12 when the base is 12. Well, according to what we just said here, this whole thing would be equal to this exponent, which is exponent 1. So that's the whole thing must be equal to 1. Here, if you want to find what's log of cube root of 3 if the base is the same, so again, that also would be equal to 1, because this would be to the power of 1. Next example, what's log of 1? Remember, I can replace 1 with a base to the power of 0, any base I want. Since the base here is 3, I can write that 3 to the power of 0 is equal to 1. If I replace this 1 with 3 to the power of 0, you can clearly see that this is the same as log of base 3. Instead of 1, I'm going to write it as 3 to the power of 0. 3 to the power of 0. So since the base of the logarithm and base of the exponent is the same, the whole thing must be equal to this exponent, which is 0. Look at this one. Log of 1 with the base 0.4. How is this equal to 0? Okay, I can write 1 as 0.4 to the power of 0. Remember, anything to the power of 0 is equal to 1. A to the power of 0 is equal to 1. So instead of A, I'm going to pick 0.4 because it matches the base here. So 0.4 to the power of 0 also is equal to 1. So if I write 1 as 0.4 to the power of 0, so this is really log of, this is base is 0.4. I'm going to replace 1 with 0.4 to the power of 0. So you see the whole thing must be equal to 0 then. Next example, log of 4 to the power of 7. If the base is 4, well, matching again, the whole thing would be equal to 7. 5 to the power of log of 6. Again, the base of the logarithm and base of the exponential is the same, so the whole thing must be equal to 6. This looks like this property here. Last example in here. What's log of 64 with the base 4? Well, I have to see if I can make 64 as a base of 4. Is 64 is a factor of 4? Sure is. 4 times 4 times 4 is equal to 64. So if I replace 64 with 4 to the power of 3, this base and this base matches. So the whole thing must be equal to 3 according to this property.